Hello, and welcome to Chapter 8, Section 2. So today we actually learn how to calculate a confidence interval and the process needed in order to make our answer complete and beautiful and include everything that we're supposed to. So here we go. So each time you are asked to construct a confidence interval, we talked about last time a confidence interval, it's that point estimate plus or minus the margin of error. Every time you're asked to do that, you have to do some checks first. So the process to help us remember this is called panic. So obviously you are not panicking, but you are panicking because when you panic, these are the 5 things you have to include in your answer. So the first thing we need to include is P for parameters. So parameters, remember, is the word for like what number are you trying to describe. So really we're just saying what number are you trying to estimate here with your confidence interval. So are we talking about a mean? Are we talking about a proportion of the population? So this is also a chance for you to insert your context of the problem. Remember, every AP problem you have to answer with context. That's a big part of your points. So this is where you're going to put that context in. The second thing we have to check for is our assumptions/conditions. So our assumptions and conditions is basically the 10% rule that we've been checking for and the large counts or the central limit theorem that we've been checking for. So each time that we construct a confidence interval, we have to make sure our data come from random independent samples. So we want to make sure we have a simple random sample, an SRS. We want to make sure we have independent samples, so that's where that 10% rule comes in. And we also want a normal distribution, and that's why we use the large counts rule or the central limit theorem to check to make sure things are normal. So these are things that you have to state so that the reader, the grader knows that like you went through the process and did everything correctly. The third thing we want to do is to name the interval. So right now it sounds stupid because we only have one name. As we add more different types of situations and the different formulas for those different types of situations, that's when we're going to learn the names of more confidence intervals. But for right now, it's just the title of this video. It's a one sample confidence interval for a population proportion. That's the only name we have so far because this is the only confidence interval we're going to be able to find thus far. The fourth thing we include is very straightforward. We actually need to calculate the interval itself. So this is the only part that's really like the mathy part. So this is where we show our work to calculate our confidence interval. And then lastly, the thing we need to include is our conclusion. So every time we calculate a confidence interval, we want to make sure the reader or the grader knows what our interval means. So we want to interpret it. And we have a pretty standard interpretation that we use just so that the context is included, we correctly interpret the interval itself so that we don't lose points on things like that. Alright, so let's actually do this process with an example. So we have a sample survey that interviewed a simple random sample of 267 college women. 75% of the sample said that they had been on a diet in the past 12 months. Construct a 95% confidence interval to estimate the proportion of college women who had been on a diet in the past 12 months. So keep in mind, when we are constructing a confidence interval, we're trying to estimate for a population based on the numbers that we got from our sample. So from our sample, we have a proportion of 75%. And we're trying to see like what the true proportion is of all college women who've been on a diet in the past 12 months. So that's what we're going to put in our parameters. We want to estimate the population proportion of college women who have been on a diet in the past 12 months. This is what we're trying to estimate, and so we state that. Next, our assumptions and conditions. So we need to check that we had a random independent sample. And they did tell us it was an SRS, so that counts for random. The independent samples will check our 10% rule for that. So writing this out, my random sample was given to me because they told us SRS, so we just have to write that it was given. Independent sample, we are checking to see that our sample size of 267 is less than 10% of all college women, which makes sense. If 267 is 10%, that would mean you'd have to have more than 2,670 college women in the world, the US. It doesn't say, but yes, for sure, there's definitely more than 2,000 something college women. And the last thing we need to check is for normality. So because we're dealing with proportions, then our large counts condition for proportions would be that n times p has to be greater than 10, and n times 1 minus p has to be greater than or equal to 10. So when you're checking this and when you're writing it out, you need to make sure you plug in your numbers to actually show, like, whatever you multiply, that it actually ends up being a number bigger than 10. And then we can do little check marks to show, like, yes, 200.25 is actually greater than 10, and 66.75 is actually greater than 10. Okay, so we've done our checks. Our name is our one sample confidence interval, and here I'm just, being lazy. I'm going to start abbreviating confidence interval as a CI for population proportion. And if you did this on the AP test as well, should be okay, because most people know for a CI it just means confidence interval. Okay, so let's start doing our calculations for the interval itself. So first, let me introduce you to the formula. So if you think back to the last video, we talked about the formula for a confidence interval is the point estimate plus or minus the margin of error, where the margin of error was the critical value times the standard deviation of the statistic. So our point estimate in this problem is the sample proportion. We signify that with a P with a little hat on top. So remember, that means it's the proportion from a sample. Our Z star is our critical value. And then our standard deviation of the statistic, this formula should look familiar because we kind of dealt with it in last chapter. When we were dealing with proportions, we would multiply the square root of p times 1 minus p over n. But now, because we don't know the population proportion, we can only do this with our sample proportion. And so that's why it's a p hat instead. Okay, so from here, once we have the formula, we just need to plug everything in. So in this problem, p hat for us is 0.75, because they told us in the sample 75% of the women said they had been on a diet. Plus or minus. Z star, remember, is our calculation of the critical value. They're asking for a 95% confidence interval. So I'll do this on the side over here because it's not quite as involved in our confidence interval here. So remember, if you want a 95% confidence interval, that means you want 95% of the area in the middle of the normal curve, which means on the outsides you want 5%. So on each side, that's 2.5%, or 0.025. So the Z-score, where 0.025 is on the left, would be 1.96. So Z star for us is going to be 1.96 times the square root of our p hat, which is the 0.75, times 1 minus p hat all over n. And n for us, our sample size, was 267. Okay, so really, when you show your work on the AP test or anything like that, you don't need to write out the formula itself. It is actually much better for you to actually plug stuff in so that way the reader knows what numbers you're actually using for each part of the formula. At this point, though, we can just multiply everything in our calculators, find the interval itself. So when we do this in the calculator, I end up with 0.0519 from this part, multiplying the 1.96 with my square root. So this number right here is my margin of error, because remember, in a confidence interval, it's the point estimate plus or minus the margin of error. So my margin of error right now is everything after the plus or minus. That number comes out to be 0.0519. Since we're talking about percentages here, we're basically saying our confidence interval is going to be 75% plus or minus 5%. We actually want the actual endpoints, though, of this interval. So we're going to take that 0.75, add 0.0519, and 0.75 minus 0.0519. So the smaller number always gets written first. So when we do that, I end up with 0.6981 as my smaller number, and when I add, I end up with 0.8019. So our interval, we usually write it like this. It's kind of like interval notation where you have the parentheses or square brackets. So we're basically saying all the numbers between 0.6981 and 0.8019, all of those numbers could be the potential population proportion. sorry, I misspoke, not the potential population proportion, like the actual population proportion, because we don't actually know what it is. It's not like something that's could be found out later. It's what the true proportion actually is. And finally, our conclusion basically sounds like this every time. We are blank % confident that the population proportion of blank, and this is where we insert our context, is between blank and blank. So the blank % confident is whatever they're asking us for. They asked us for a 95% confidence interval, so our percentage there is going to be 95%. And then we're saying that we are 95% confident that the population proportion of college women who have been on a diet in the past 12 months is between, and then these are the two numbers for our interval. So we're talking about 0.6981 and 0.8019. So using those numbers, because we were dealing with 75% in the beginning of the problem, we're going to turn these into percentages as well. So 69.81% and 80.19%. So we're basically saying the true proportion, or the population proportion, is somewhere in between these two numbers based off of this sample. Alright, so each time we do a construct a confidence interval problem, it's going to look something like this. We want all 5 of those steps included. So now I want to talk about a question that relates to the last problem that we did where we calculated the confidence interval. So this time, the nutrition department at this college claims 70% of college women have been on a diet. Does this seem reasonable? So here, remember from our problem before, we were saying 75% of the sample had said they were on a diet. So now the nutrition department is trying to claim a different number, 70%. So they're saying this 70% is trying to talk about the whole population. So based on whatever studies they did, blah, 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 they're saying 70%. Does this seem reasonable based off of our sample? So remember, in our confidence interval, we were saying the true proportion, the percentage, should be between 69.81% and 80.19%. So we're saying the true proportion, the true population proportion, should be somewhere between those two numbers. So if they're claiming 70%, we want to figure out basically, does that number that they're claiming fall within our interval? Because if it does, then it does seem reasonable. If it doesn't, then it's probably not. So we could answer by saying this is reasonable because 70% falls within our 95% confidence interval. So keep in mind, our 95% confidence interval meant that we were 95% confident in our numbers. So this is good. And we also said that we have like a good sample. We got a random independent sample. So based on our sampling skills and our calculations, the 70% number does seem reasonable. However, I do want to warn you that that 70% that they're claiming might not necessarily be true. There's 5% where we're not being confident. So it's reasonable, but just know that it's not necessarily true. The last example that I want to do in this section is an example where we need to solve for a sample size. So here, they're asking, I'm going to use the same problem as before for the context of this problem, but let's say we want the margin of error to be at most 0.01, or like 1%. So what we're basically saying is that we want that margin of error to be smaller. Our margin of error earlier, when we calculated this, was like 5%, 0.0519. So if we want that margin of error to be smaller, meaning we want our interval of numbers to be more narrow, then we would need to increase our sample size in order to do that, because we want more consistency, basically, is what we're saying. So in order to get that consistency, we need to increase our sample size, but we want to know exactly how far we need to increase our sample size by, because in real life, increasing a sample size is harder to do, because you are now required to find more people. That's still a random independent sample. So, more work. So what we want to do is use algebra to calculate n. So we know the margin of error formula is z star times the square root of p hat times 1 minus p hat all over n. So remember, the margin of error is everything that comes after the plus or minus. So this section right here, the critical value times the standard deviation of the statistic. So if I know I want my margin of error to be at most 0.01, then I can set this up as an inequality less than or equal to 0.01. So we're going to assume that the z star here is still at the 95% confidence level. In any problems that you do like this, they would tell you what confidence level to use so that you know what z star to use. But for the sake of this problem, I'm just going to leave that the same. So we would still be using 1.96 as our z star. Our sample proportion would still be the 75%. But now we don't know what n is because we're being asked what sample size should we use. So it's not going to be 267 anymore. And all of that is less than or equal to 0.01. So from here, we're doing algebra. Here we go. I'm going to start, because we want to get n by itself, I'm going to start off by dividing both sides by 1.96. So obviously we would do that part in the calculator, but when you do things in the calculator, keep in mind you want to keep all your decimals for as long as possible. Don't round your numbers until the very end, otherwise you're going to be off at the very end. From here, we want to get n by itself, so I can square both sides to get rid of that square root. And then we end up with 0.75 times 0.25 over n, but we need n to not be in the denominator, so let me multiply both sides by n. That way it's no longer in the denominator. And then to get n by itself, I would just need to divide both sides by this 0.01 over 1.96 squared. So I'm going to end up with 0.75 times 0.25 over... Okay, so this, if I type this in the calculator, then I can get to the most accurate rounding at the end. Or, because I'm writing this out kind of long way, in the calculator, if we were to do this, we can start off by, our first step was to divide both sides by 1.96. So let me just do that here, 0.01 divided by 1.96. And then we want to square this number. So our graphing calculators have this fancy thing where you can copy paste. So if I scroll up, highlight it and hit enter, that'll copy paste the number for me, and then I can just square it like that. Another way to do that is this ANS here, that's in blue, so second and then the negative sign will give ANS. This stands for the last answer that you got. So even if you don't have that copy paste function, you can still use this to square the answer that you last got. Okay, we get some crazy number here, which is fine, I don't care, because we're just going to keep copy pasting to keep all our decimals okay. And keep in mind this E right here, this is just scientific notation, so they're basically saying move the decimal place 5 places to the left. So this is actually like 0.000026 blah 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 blah. Okay, but I don't care about that because I'm just going to keep using whatever number the calculator gives me. After we square it, we wanted to divide the 0.75 times 0.25 by that number. So I'm going to type it as 0.75 times 0.25, oops, in parentheses, so that I can multiply that first, divided by that crazy number. Hit enter, I end up with 7,203 for n. So that means n has to be greater than or equal to 7,203. So keep in mind, it's a greater than or equal to sign for the n. So that means for this number, whatever you solve for n, if you end up with a decimal, let's say this ended up being like 7,203.1 or something like that, n still has to be greater than or equal to that. And we can't have 0.1 of a person. So in general, even anytime you end up with a decimal for n, you're going to have to round up to the next whole number. For us, we ended up with 7,203 exactly, so there's no rounding needed. Our answer would just be that our sample size needs to be at least 7,203. If you ended up with a decimal, then our answer would be that our sample size would need to be at least 7,204. So no matter what the decimal is, whether the number is bigger than 5 or less than 5, you're always rounding up to the next whole number. All right, That's it for this section. Thanks for watching. Don't forget to like and subscribe. Bye.